Right, we're going to do some applications of double integrals now before we go on to triple integrals. And there's really two main applications we're going to look at. First, we're going to look at density and mass, moments, and center of mass. And we're also going to look at surface area. So the next two videos are going to be over density and mass and moments and center of mass. We could actually go further with this. If you read the book, they go into second moments and moments of inertia, but there's so much material to go over this semester that I think it's just enough. We'll just go over total mass and center of mass. So the idea behind this is a very common problem in physics. It's if you have a distribution of something, and the two typical examples given are mass distributed across either a two-dimensional plate or three-dimensional region in space, and you have a density function. So it tells you the instantaneous density at a point. So what that means is if you were to take smaller and smaller boxes or spheres centered around that point, what would be the density as you get closer and closer to that point in the limit? So you can have like kind of an instantaneous density function at a point. And can you take that density function and find the total mass? This is similar to a problem that's done in Calculus 1. So the first semester, you do it in one dimension. So you're given just a, like rho of x is just a function of x. You have a metal rod or something that has density, and you integrate the density to find the total mass. So all we're doing here is we're just upping it one dimension to 2 dimensions, and later we'll up it to 3 dimensions. The other example that's given a lot is if you have a charge density function over some region, if you integrate the charge density, you get the total charge over that region. The calculation and mathematically, it's identical to the problem of solving for the total mass given the mass density. In the next video, we'll talk about moments and center of mass, which is kind of going over then where is the mass centered at. But for now, we're just going to do density and mass. So let's start off with, suppose we have a region here. So I'm going to draw a region. And we can call this region, say, D. And so we're given a density function. So let's call that rho of xy. So rho of xy is the density at the point xy. And I want to take this density function over D and see if I can find the total mass of the region. So we're going to go through a process that should remind you very much of the process of finding Riemann sums for functions of two variables. So we're going to chop up this region into pieces of rectangles. So we're going to have a rectangular grid we're going to impose upon it. And then we're going to evaluate the density function at each point and multiply by the area, because when you multiply the density times the area, that gives you the mass in that little sub-rectangle. If you add all those up, then you get an approximation for the total mass, and then in the limit, the exact mass then would be the limit, which is the double integral of the density function. Okay, so let's assume that we've subdivided this into n subrectangles. And let's say this is one of them, say right here. So what we want to do is approximate the total mass just inside that single subrectangle there. So let's say that this is the, kth subrectangle. So I'm not going to be indexing these, with I and j in both directions. Let's just say, there's n of them, and I just say this is the kth one out of the n. So this is the kth subrectangle, and let's say that we have a delta A sub k is the area, and we're going to take a sample point inside here like x, xk star, yk star. So the mass of this little subrectangle Well, the mass of the subrectangle would be the density, so it'd be the mass density, per unit area, times the area. So times the area of that little subrectangle. But we know we could choose the sample point here. We could evaluate that density. So the mass is going to be approximately equal to that density evaluated at the sample point times the area, which we said was delta A sub k. So that's the mass of that little subrectangle is approximately equal to that. That means we get an approximation of the total mass. Approximation of the total mass is going to be the sum over all the little subrectangles, so say k equals 1 to n, of rho evaluated at that sample points times each of the little areas. But of course this is a Riemann sum. This is the whole point. This is the same type of Riemann sum that we got when we were doing the problem of finding the volume under the graph of a function of two variables. So as we let as we let n go to infinity and the areas, the delta AKs, go to 0, this is going to become the double integral, and so that's how we're going to define the total mass over this region. So we define the total mass over D to be equal to the double integral of the density function over D, dA. So it just becomes a double integral. All right, so let's look at a couple examples. So we're going to find the total mass in the triangular plate in the first quadrant bounded by x plus y equals 4, given the density function 1 plus x plus y. So first let's make a quick drawing of this. Okay, and we've got rho of xy is 1 plus x plus y. So let's set up the double integral. So we could do it either way, really. I'll do it as a type 1 region. So we'd have x is going to go from 0 to 4. And then y is going to go from 0 up to, so this is x plus y equals 4. If I solve that for y, y is equal to 4 minus x. So from 0 up to 4 minus x, and we're integrating 1 plus x plus y dy dx. So this is a good practice problem just to practice evaluating iterated integrals. So if you want to go ahead, pause the video. I'm actually going to write out all the details here. I'm going to pause the video and write out all the details. So you should pause it, work this out, see what you get for the value of this iterated integral. So here's the calculation. You should have gotten 88 thirds. So you can go ahead and check through your work, see that it matches mine here. So that's 29 1/3. We can do a little gut check on the approximate value of this. If you go up to the region here, so the maximum value of 1 plus x plus y, of course, is going to be 5 along the hypotenuse of this right triangle. So it looks like this function that we are integrating varies between 1 and 5. So, kind of middle value there would be about 3. So if we multiply kind of that middle value of 3 by the area of this triangle, we should get something close to what we got. This is just to see if this is like a ballpark figure. So it should be like 3 times the area, which would be 1/2 base times height, so 4 times 4. And so this is 24. So, within a reasonable ballpark figure of 29 1/3. So, it's always a good idea in these problems to kind of just, think about what's going on, see if your answer is reasonable or if it makes sense. And so here, it seems like a reasonable answer. All right, for this next problem, we are going to find the total electric charge given a charge density function. So this is exactly the same kind of problem. The only difference is instead of using rho of xy, we use sigma of xy, and the total charge is notated with q instead of m. So otherwise, it's pretty much the same problem. So let's see. So distributed over the analyst. So an analyst just means it's just a ring. So it's just the region between two concentric circles. So in this case, they're circles centered at the origin. So if we draw a nice little coordinate system here, we can graph two circles here. So this is perfectly set up for polar coordinates. So if we're integrating this, we want to go theta from 0 to 2 pi, and r is going to go from 2 up to square root 6. Be careful, whenever you have this x squared plus y squared kind of quantity, and you're converting it to polar coordinates, remember that that's r squared, so I have to take the square root here. It's a real common mistake just to go from 4 to 6 instead of from 2 to square root 6. And we're integrating 8 minus x squared plus y squared, so that's going to be 8 minus r squared, right? Because this is minus x squared plus y squared. And we have to integrate r dr d theta. Okay, this is another pretty straightforward iterated integral. So we're integrating 8r minus r cubed dr d theta. And we've seen this a few times. This happens especially with these other coordinate systems like polar coordinates and with cylindrical and spherical coordinates later. Since this is solely a function of r, we can just cancel those out. We pick up a factor of 2 pi, and I'm going to try not to forget it this time. So we get 2 pi times, okay, this is going to integrate to 4r squared minus r to the 4th over 2, sorry, r to the 4th over 4, between 2 and square root 6. That's going to be 2 pi times, let's see, that's going to be 24 minus 36 over 9, so minus, sorry, 36 over 4, which is 9, minus, just keep your parentheses straight here, 16 minus 16 over 4 minus 4. All right, we're just about there. 2 pi. All of the stuff in here is, let's see, 15, 12. 15 minus 12 is 3. So this works out really nice. It's just 6 pi. So 6 pi is the total charge inside this region. All right, so mathematically there's not much new going on here, but in the next video we will see something that's going to be a new idea as far as the physics is concerned. We're going to talk about moments and the center of mass. The center of mass is where the mass is kind of centered around, where it would balance perfectly. And so we'll go over that in the next video. We're going to continue our study of masses and density functions. And what we're going to talk about in this video is something called the center of mass. So if you have a two-dimensional plate or lamina, the center of mass, the best way to think about what that is it's the point at which that plate would perfectly balance. So if you were to just prop up the plate, then it would perfectly balance right at that point. So how do we go about figuring out the center of mass? So this is a problem that I believe is covered in second semester calculus. So you should have seen it when you took Calc 2. But if you don't quite remember it or you didn't see it at the time, I'll go over how you compute this. The way we do this is to calculate what's called the moments about the coordinate axes. So the moment of a point particle would be the product of the mass of that particle and its distance to an axis. And so what we're going to do is figure out the entire moment of the plate. We're going to add up all the little moments of little pieces of it. So it's very similar to what we did for the mass. We chop up this plate or lamina region into a bunch of little rectangles. We compute the moment of each little subrectangle. We add up all of those and treat each of the subrectangles then as if they were a single point. And we add them all up, we get an approximation to what we should consider to be the moment of the entire plate or lamina. And then we take the limit as the number of rectangles goes to infinity and the area of the subrectangles goes to 0, and we get a double integral. And that double integral is going to define the moment about one of the axes. And those moments are what are going to allow us to define the center of mass. So let's start with the moment around, or the moment about, the x-axis. So, okay, so I just literally copied and pasted the picture that we had from the previous video here. It's exactly the same. We've got n little subrectangles for this region D, and we're focusing in on this kth subrectangle with area delta AK, and we're taking a sample point xk star yk star. So we want to figure out what's the moment about the x-axis of this kth subrectangle. So the way this is defined is it's the product of the mass and the distance to the x-axis. So it's the mass times distance to the x-axis. Now we have to approximate both of those things. Now the mass, first of all, the mass is the mass density per unit area times the area. So this is very similar to what we did in the previous video when we were just computing mass. But then it's also times this distance to the x-axis. So we can approximate the mass density per unit area by just evaluating the mass density function somewhere at this sample point. So that's going to be rho of xk star, yk star. And then we multiply that by the area, which is delta A sub k. So this times the distance to the x-axis. Well, the distance to the x-axis is the y-coordinate, and we'll choose the y-coordinate of the sample point. So what we end up with is, if I kind of just rearrange this a little bit, I could write it as yk star times rho at the sample point times delta A sub k. Okay, now that's an approximation for the moment of just the mass that represents this little subrectangle. So what we want to do is do this for all the different subrectangles and add them up, and that'll give us an approximation to the moment about the x-axis of the entire lamina, or the entire plate. Okay, and that will be then the sum. So sum from k equals 1 to n, just add them all up. And now take the limit as we let the number of rectangles go to infinity and the areas go to 0. And this will give us, this is our definition then of the moment about the x-axis. And the notation we use for this is capital M sub x. So it's a little confusing at first because the subscript is x, but we end up integrating y. And the best way to think of it is the x indicates the axis that you're taking the moment about. Well, in order to calculate the moment about the x-axis, you need to know the distance from the x-axis, which is actually the y-coordinate, not the x-coordinate. That's really the best way I can think about it so you don't get mixed up the subscript. So m sub x is going to be the double integral over d of y times rho of xy dA. And similarly, we can define the moment about the y-axis. just interchange the role of x and y. So this is m sub y, and it's the double integral over d of x, rho of xy dA. So those are the moments. Now, how do we define the center of mass? Well, what we want to do is find the coordinate value so that if all of the mass was concentrated at that one point, then it would have the same moment as the entire plate or lamina does. So a good way to think about what the center of mass is, so let's say we want the x coordinate of the center of mass. Well, what we're kind of doing there is we're taking the moment about the y-axis, m sub y, and you can almost think of this as it's going to be the average distance to the y-axis over the entire lamina. So what you'd have to do is, it's almost like a weighted average, and it's weighted by the density function. So normally, if you just wanted to find the average value of x, the distance to the y-axis, you just double integrate x dA, and you divide by, the area. But we want it to be weighted because the mass is going to be, there's more mass in certain places compared to others because the density function is bigger compared to other places. So we want the average of the x coordinates, but we want it weighted by the mass. So if there's more mass in one place, that's going to count for more. And so we're going to end up dividing by the total mass in the same way that we would divide by the total area if we were just computing an ordinary average value. So I'm trying to kind of give a physics explanation about this. To really understand this, probably it's best in a physics class to really delve into the reasoning behind it and why it works. But what we end up doing is we're going to define, so the x coordinate of the center of mass, we're going to call it x bar. So this is going to be m sub y, right? So it's the moment about the y-axis divided by little m. And the y coordinate of the center of mass is going to be the moment around the x-axis divided by little m, where little m is the total mass, which is just what we did in the last video. So the little m is the total mass, which is just the double integral over d of the density function. Okay, so another way you could write this, see if I have enough room here. Nope, not quite. Well, I'll write this on, when we get to the next one, I'll write out exactly what this looks like when you put, one on top of the other. So this means we get center of mass then is equal to x bar y bar. Okay, let's look at a couple examples. I think after working through a couple examples, it will start to make more intuitive sense. All right, so we're going to find total mass and center of mass of the plate occupying triangle vertices at the origin, 1, 0, 1, 1, and our density function is going to be xy. So first, before we get started with this particular example, let's just kind of write down everything, the formulas that we need here. So start with the mass. So the mass is little m. This is what we were doing before. It's just the integral of the density function dA. Then we've got m sub y, which is the double integral of x, rho of xy dA, and mx, the double integral of y, rho of xy dA. And this means that, so x bar, the x coordinate of the center of mass, then, is m sub y over little m. Now let's write out exactly what that is there. So it's going to be the double integral over d of x, rho of xy dA, divided by the double integral over d of rho of xy dA. So notice This is very similar to an average value. It's almost like we're finding the average value of the function x. The difference is that there wouldn't be this row of xy in there. And in fact, in Calc 2, you do this kind of problem, but you do it with constant density, and the row is a constant. You may remember this from Calc 2. You do this kind of problem, and row is just a constant. It gets pulled out on top, it gets pulled out on the bottom, and then the rows cancel, and they just kind of magically go away. So the only difference now is instead of row being a constant, it's a function of x and y, so we have to integrate it. So we're kind of taking a weighted average of x, where it's weighted by this density function. And the same thing with the y-coordinate of the center of mass, m sub x over little m, is like a weighted average of the y-coordinate, where we're weighting it by the density function again. Okay, so let's start off here. It's always good to start with the mass first. It's usually the simplest one, and you're going to need it for both coordinates. So let's go ahead and find the mass here. So the mass is the double integral of rho of xy. So we're finding the double integral of xy dA. Now the limits, okay, so let's kind of go off to the side here and draw a little picture here. So it's the triangle with vertices at the origin. Okay, so there. And at 1, 0, there. And I believe the other one was at 1, 1, 0, 0, 1, 0, 1, 1. Okay, so it's going to be up here. And this triangle, so I just need to connect these now. Okay, so this region. Okay, so should we do this as a type 1 or type 2? I think type 1 is probably better. So for fixed x, let's see, this is, it's y equals x. Okay. So we're going to go x from 0 to 1. And then for fixed x, y goes from 0 up to x. So the integral from 0 to 1, the integral from 0 to x of xy dy dx. We integrate with respect to y first. So that's going to be x, y squared over 2 from 0 to x. So that's the integral from 0 to 1 of x cubed over 2 dx, which is going to be x to the 4th over 8. X to the 4th over 8 from 0 to 1, which of course is 1/8. So that's the total mass. So the mass is 1/8. Now, that doesn't tell us the center of mass. To do this, we need to find the moments. So let's go ahead and figure out the two moments. So we start with the moment about, it doesn't really matter which order you're going. I'm going to do the moment around the y-axis. So this is double integral x. Okay, so we're 0 to 1, 0 to x. It's x times xy, so that's going to be x squared y dy dx. Again, with respect to y, we get x squared y squared over 2 from 0 to x, which means we're integrating x to the 4th over 2, which is going to give us x to the 5 over 10. Okay, x to the 5 over 10 from 0 to 1, which is 1/10. Okay, so 1/10 is the moment about the y-axis. Let's do the moment about the x-axis. And 0 to 1, 0 to x. But now it's y times xy, so xy squared dy dx. So let's see, 0 to 1, xy cubed over 3 from 0 to x. And that's going to be 0 to 1 of x to the 4th over 3, which finally is going to be x to the 5th over 15, from 0 to 1. So we get 1/15 for the moment about the x-axis. So now we can put everything together. Actually, let me go up here and let me box the total mass. All right, now let's go and figure out the center of mass. So x bar m sub y over little m. So that's 1/10 divided by 1/8. All right, that's 8/10. 4/5. Y bar is m sub x over little m, which is 1/15 divided by 1/8. 8/15. So that's our center of mass. So x bar y bar is equal to 4/5, 8/15. All right, so this one, the calculations were pretty simple in this one, mainly because I wanted to go over just the idea of it and have you get a feel for what the center of mass means. So, by the way, we can go up here and actually let's see where that center of mass is. Remember, so the density function was x, y, which means the largest the density function is going to be up there at the point 1, 1. Okay, and so 4/5, 8/15. So that's going to be, roughly about here. 4/5 is going to be about there. 8/15. I'm guessing right about somewhere around there, which seems to make sense. It's roughly in the middle, but it's more slanted to the upper right corner of this triangle, which makes sense because there's more mass over there. There's almost no mass in the lower left corner, and there's most of the masses in the upper right corner. So that seems like a reasonable answer. So the next problem is going to be much more computationally intense, and it's going to be more difficult to set up. In fact, the integrals are kind of so involved that we're going to use the integral calculator online to do it because we get these big powers of cosine. So this says we're going to find the center of mass of the crescent-shaped lamina consisting of the region outside the unit circle and inside the cardioid, r equals 1 plus cosine theta. So one of the boundaries of this region is actually given in polar coordinates. So we're definitely going to use polar coordinates here. And it says, given that the density function is proportional to the distance from the origin. So they're not even giving an explicit formula for the density function. They're just saying, well, it's proportional to the distance to the origin. So what we're going to do is introduce a proportionality constant, and what we'll see is that constant will end up washing away in the end. So we'll keep it throughout all the computations. We'll call it, say, k. But in the end, when we're actually going to compute where the center of mass is, it's not going to matter. And it says you may use an integral calculator to evaluate definite integrals. So what we're going to do is we're going to get to a point where there's going to be an integral of something that's really, it's going to have like a cosine squared, cosine cubed, cosine to the 5th. It's going to have a lot of powers of cosine. And so then we'll just go online and evaluate that. There's no point in, it's a calculus 2 technique, doing powers of sine and cosine. It just ends up being a mess, and that's not really the point of the problem. So let's set this up. So outside the unit circle, so let's draw a unit circle here. All right, so there's our unit circle. Now, this cardioid, here's what it looks like. So we start off at, so when theta is 0, we start off at 2. And then as we get to pi over 2, we're going to decrease all the way down to 1. So this is going to kind of curl around here. Then between pi over 2 and pi, cosine is going to go from 0 to -1, so this is going to go from 1 down to 0. So it's just going to kind of fold in on the origin. So something like this. And then between pi and 2 pi, it just kind of has the same shape just below the axis, because it goes from 0 back up to 1, back up to 2. So it ends up looking something like this. Okay, so more or less like this. And so we want the region that is outside the unit circle and inside the cardioid. So that's going to have to be this whole region here. All right, so that's our region. Now let's go over what our limits are going to be. So our limits of integration. Okay, so it's going to be the integral from. So what we want to do is start off down here, and that's going to be at theta equals minus pi over 2. We want to get this all in one sweep. So we're going to go from minus pi over 2, which is going to give us radius 1, all the way to 0, radius 2, and then to pi over 2, where it would give us radius 1 again. And so that's going to be all the way up to here at pi over 2. So we're going to integrate from minus pi over 2 to pi over 2. And the radius has to go between 1 and 1 plus cosine theta. Right, this is what one of these looks like. If I start at the origin, I go out this way. You know, say this is a theta. I'm going between r equals 1. The unit circle has equation r equals 1. And this is r equals 1 plus cosine theta. So 1 to 1 plus cosine theta. And then don't forget that I'm going to have to include the RDR here. And what is our density function? We're not given explicitly what it is. But our density function is going to be proportional to the distance from the origin. Well, what's the distance from the origin? That's just r. That's what polar coordinates are. R is the distance from the origin. But it's proportional, so we'll put in a proportionality constant. Let's call it k. So our density function is going to be k times r. So with all this setup out of the way, now we can finally start to do some of these calculations. So let's find the total mass. So the total mass is going to be the integral from minus pi over 2 to pi over 2, 1 to 1 plus cosine theta of, we just integrate the density. So we just integrate kr times r dr d theta. So the k can come all the way out. That's a constant. So we got k times the integral from minus pi over 2 to pi over 2, the integral of r squared. So it's going to be r cubed over 3 from 1 to 1 plus cosine theta. We're going to be cubing it. Yeah, this is already too much that it's worth writing it out. So, okay, let's clean it up as much as we can. We've got k over 3. Now, what's left over here? So it's going to be the integral from minus pi over 2 to pi over 2 of 1 plus cosine theta cubed minus 1. Okay, all of this d theta. Now we can still clean this up a little bit more. It's k over 3 times the integral from, now notice that this is, remember we talked about being on the lookout for even functions. This is an even function because it's just got cosines in it. If you put in minus theta, you get the same thing. So that means we can really go from 0 to pi over 2 as long as I include a factor of 2 out here. So I'm going to do that. And now if I multiply this out, if you remember the binomial theorem, this is going to be 1 plus 3 cosine squared plus cosine cubed, but then it's minus 1. So what I'm left with, if you multiply this out, is 3 cosine plus 3 cosine squared plus a cosine cubed. Now, this is not impossible to do. obviously the cosine term, that's not hard. Cosine squared, use an identity. The cosine cubed, right, so if you remember how to do these, you want to, take a cosine squared, change it into 1 minus sine squared. It's just kind of tedious, and it's not really the point of the problem. So we're just going to go ahead and punch this into an integral calculator. Oh, right. So this is such a nice website. I wish they had this when I was taking calculus, but it's a different time. So 3 cosine theta plus 3 cosine squared of theta plus cosine cubed of theta. Check to make sure they got syntax right. 3 cosine squared plus cosine cubed. We need to change this to, there's theta way up there above x. Okay, so we'll change it to theta, and that was a definite integral from 0 up to pi over 2. All right, go gadget integrator. Reload. Okay, I don't know why I had to do that. Go. For some reason, this web page is taking way longer than it ever used to. I've been using it for a few years. Okay, finally. Oh, that took entirely too long. Okay, so we're going to go down. There we go. So it's 9 pi plus 44 all over 12. Okay, so that's 9 pi plus 44 all over 12. Okay, so there's a little bit of canceling here. 6. So it's 9 pi plus 44 all over 18. Okay, and once again, this is the total mass. Okay, so now let's get the moments. Okay, the moment about the y-axis. This is the integral from minus pi over 2 to pi over 2. 1 to 1 plus cosine theta. Now, you have to multiply, we're going to integrate, now we're going to integrate x, which is r cosine theta, times rho, which is kr, times r dr d theta. So there's 3 r's in here. So this is the integral from minus pi over 2 to pi over 2. The integral from 1 to 1 plus cosine theta of k times, so it looks like we've got an r cubed and a cosine. So that's r cubed cosine theta dr d theta. All right, so once again, let's clean this up. We're integrating with respect to r, so that's going to be r to the 4th over 4. The cosine is going to come, so the cosine can come outside the innermost integral, because it's a constant with respect to r, but it can't go all the way out because it's still a function of theta. So we can pull the cosine through one of the integral signs, but the r to the 4th over 4, we can pull the 1/4 all the way out. So what we end up with is k over 4 times the integral from minus pi over 2 to pi over 2 of cosine theta times r to the 4th evaluated from 1 up to 1 plus cosine theta d theta. So this is going to be way more of a mess. All right. So it's going to be k over 4 cosine theta times 1 plus cosine theta all to the 4th minus 1. All right. I think we have enough room here, just enough. K over 4 Now again, you have to remember kind of the binomial theorem here. This is the integral from minus pi over 2 to pi over 2. So inside the brackets, there's the coefficients are 1, 4, 6, 4, 1. So think of Pascal's triangle, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So the 1s cancel out, but then the first term we do get is 4 cosine plus 6 cosine squared plus 4 cosine cubed plus cosine to the 4th. Wow. Who wants to do this by hand? Not me. So let's take a look at what we got here. Again, these are all even. This is all even. It's all cosines. Nothing but cosines. So we'll that k over 4 on the outside will now become k over 2 because we're multiplying by 2. So we got k over 2, the integral from 0 to pi over 2 of 4 cosine squared plus 6 cosine cubed plus 4 cosine to the 4th plus cosine to the 5th. This is what I was saying about there's all these ridiculous powers of cosine, which is possible to do, but I'm not going to do. So let's go back to the integral calculator and figure out what it says this is. All right, so we got to go back up here. All right, so it's going to be 4 cosine squared, so I got to change this squared, plus 6 cosine cubed, plus 4 cosine to the 4th, plus a cosine to the 5th. Okay, let's just double check here, make sure, does that look right? 4 cosine squared, 6 cosine cubed, 4 cosine to the 4th, and a cosine to the 5th. Great. And it's from 0 to pi over 2 still. So go, and we hope it takes less than 2 hours. Okay, that didn't take nearly as long. Wow. Who wants to do that? There it is. Okay, 105 pi plus 272 all over 60. Good grief. Okay, so let's put that in. All right, so this gives us there's not a whole lot we can do with this. 105 pi plus 272 k all over 120. All right, now I'm going to claim that m sub x is equal to 0. Now I'm going to pause the video. Think about conceptually, just from a physics standpoint, why the moment about the x-axis has to be 0. So hopefully what you're able to reason through is that, first of all, this region is symmetric about the x-axis. But not only that, the density function is k times r, and that density function is also symmetric about the x-axis. So if the region is symmetric about the x-axis, and the density function is symmetric about the x-axis, I mean, think about it. This is saying where's it going to balance? The region and the density, the whole thing is symmetric about the x-axis. It's got to balance on the x-axis. Now, that's just a physical, intuitive kind of reasoning. But, you can work through, we can set it up just enough to see that it's going to be 0. So I'll just kind of go through enough here. So we can start off like we did with the previous one. We're not going to have to go nearly as far, though, because we're going to reach a point where we're going to be able to see that it's 0. So instead of r cosine, we would get r sine. So that's the key. It's r sine, not r cosine, times kr times r dr d theta. Okay, and again, we can take out the k. Because this is, I'm just kind of following just what we did in the previous moment about the y-axis. So now we've got r cubed sine of theta dr d theta. And again, I can take out the 1/4. But now the sine comes out. So I've got sine of theta times r to the 4th from 1 up to 1 plus cosine theta d theta. Now, stop right here. What is this bracket r to the 4th? So evaluating r to the 4th from 1 to 1 plus cosine theta. That's going to involve, that's just going to be an expression involving just cosines. So whatever that turns out to be, in fact, we see what up here, it's 1 plus cosine all to the 4th minus 1. But that piece right there, this is all even, just like before. However, the sine part is odd. Well, what's an odd times an even? An odd function times an even function is odd. So we're evaluating an odd function from minus pi over 2 to pi over 2. That's got to be 0. So that's the mathematical reason why the calculation ends up being 0. But hopefully you also understood physically, from the physics standpoint, why it has to be 0 as well. Okay, so the only thing really to figure out here, we know that the y-coordinate is going to be 0 because it's going to be, so the y-coordinate is mx divided by the mass, so that's got to be 0. But the x-coordinate is going to be this, so it's going to be this mess right here, divided by the total mass, which was also another mess up here. Now, notice when you divide those, the k's are going to cancel out. So it's going to be, I think we have just enough room down here. So x bar is going to be equal to 105 pi plus 272 k all over 120 times, and now I'm going to flip this because I'm dividing by it, so it's times 18 over 9 pi plus 44 k. And there's a little bit of canceling, not too much, so there's not like there's a whole, it's not like this comes down to, 3 pi or something. 18 over 120, okay, that's going to make 3 over 20, and that's about all we can do. So that's what x bar is. It's just 3 times this 105 pi plus 272 all over 9 pi plus 44. There's really no other nicer way to write it. Okay, so finally we can write x bar y bar is equal to, 3 105 pi plus 272 all over 20 9 pi plus 44, comma 0. Now this is approximately equal to 1.249. Okay, so if you evaluate that on the calculator, the x-coordinate is just a little bit less than 1 1/4. So let's go up here, let's check. Does that seem to make sense? 1 1/4 would be right about there. So this seems pretty reasonable. The density increases from 1 kind of gradually out to 2. But, as you get further out there, there's less of the mass out there. So it makes sense that it's a little bit closer to 1 than it is to 2. And, of course, we reasoned that it had to be on the x-axis. So that's where that is. So let's go and circle that. So this was a pretty involved problem, obviously, compared to the last one. This is not something I would give on an exam problem. Don't worry about that. But, you know, for a more challenging homework problem, I don't think it's out of the realm of expectation. You just have to, understand what it's saying, set everything up right, and then, use the fact that I said that it's okay to use an integral calculator to do the calculations. There's no reason to go through all these higher powers of cosine and, spend 20 minutes doing a bunch of integrals when you just make one little mistake. It's going to mess it up. So anyway, I hope you enjoyed this problem. This is a really, I think it's an interesting region, and it's a kind of natural density function to think about to figure out where the center of mass would be here. All right, then the next video, we're going to talk about surface area, another application, and then we're going to go on to triple integrals after that. So we're going to return now to this problem of calculating total mass, moments, and center of mass, except we're going to up the number of dimensions by 1 now. So instead of looking at a 2-dimensional plate or lamina, we're going to look at calculating the mass, the moments, and the center of mass over a 3-dimensional solid region given a density function of 3 variables. So the computations here are really similar. The main difference is that instead of having 2 moments about each of the coordinate axes, the x and y axis, we have 3 moments about each of the coordinate planes. So the xy plane, the xz plane, the yz plane. But really, it's very similar idea and very similar type of calculations. So what I'm going to do here is just draw a general picture of what's going on, and then just write down the formulas, and you'll see how they're very similar to what we did before. So let's start off with, we're going to be given a 3-dimensional solid region, E, and a density function, a mass density function, rho of x, y, z. Now this could also be a charge density function where we're calculating the total charge. It's mathematically the same. So the formula for the mass, then, little m, is then the triple integral over E of the density function. So just as in 2 dimensions, the total mass was the double integral of the density function, here it's the triple integral dv. Now, we need to be a little bit more careful about the moments. So there are 3 moments about each of the coordinate planes. So let's start with the moment about the yz plane. So we'll call this m sub yz. Now, this yz is saying it's the moment about the yz plane, and a point xyz, let's say this is a point xyz up here. I should be able to project it onto the yz plane. So just imagine, it's really hard to draw this in 3 dimensions, but imagine this getting projected onto the yz plane. That's going to have coordinates 0, y, z. And the distance then from this point xyz to the yz plane is just going to be x. So the directed distance again. So it's the signed distance. So to find the moment, we went to triple integrate over this region x times rho of xyz. Just as in 2 dimensions, we would double integrate x times rho of xy, here it's a triple integral of x rho of xyz. And then we have the same thing for the other 2 coordinate planes. So for instance, in the xz plane, let's say that this projected all the way over to here. So the projection onto the xz plane then is going to have coordinates x, 0, z, and its directed distance to that plane will be y units, which means m sub xz will be the triple integral of y, rho of xyz, dv, sorry. And of course the same thing then for onto the xy plane. You start to see the pattern here. This would be z times the density. And this point would go, so let's say it goes down to that point there. And I think it's helpful to kind of put everything together here and just see what these formulas look like in terms of the two triple integrals. So then for x bar, so the x coordinate of the center of mass, then this will be the moment about the yz plane divided by the mass. So it's going to be the triple integral over E of x times the density divided by the triple integral of the density. So I hope you can see how this is really similar to two dimensions. Instead of a double integral, we have a triple integral. Instead of, dA, it's dV. But whatever coordinate you're trying to find, that's the factor that you have to multiply in the numerator. So if you're trying to find the x coordinate, x bar, then you're multiplying by x in the integrand in the numerator. If you're trying to find y bar, the y coordinate of the center of mass, then you multiply by y. So this would be, for instance, mxz over little m, the triple integral of y, total mass, and then for the z coordinate, similar, xy. All right, so these are all the formulas. So we're going to look at two examples, and these are in rectangular coordinates. We haven't gotten to cylindrical or spherical coordinates yet. And one of them is going to be over a rectangular region, so a three-dimensional box, but the lengths of the dimensions are going to be given by A, B, C instead of specific numbers, so we're going to get a general formula for it. Then the second problem is going to be to find the centroid of a region. So the centroid, you might remember from Calculus 2, that's what you calculated in Calculus 2, where you were assuming that the density was constant. If the density is constant, then the center of mass is what's called the centroid of the region itself. So two different problems. So let's go to the first one. So we're going to look at the solid rectangular region. So this is kind of a general kind of rectangular region that's with one corner at the origin, and it's in the first octant. So x goes from 0 to A, y goes from 0 to B, z goes from 0 to C. So you could have just arbitrary upper limits there. And we're going to find the total mass and center of mass if the density function is just x plus y plus z. Now, because of the symmetry in x, y, and z, it turns out that we're going to minimize some of the calculations so we can do one of the moments, and then if we just permute the variables and the parameters, then we'll get the other one. So it looks like this is going to be a little bit more work than it is, but we're actually able to use the symmetry in the problem. Okay, so let's look at let's find the mass. So little m. So this is going to be the integral from x equals 0 to A, integral from y equals 0 to B, z equals 0 to C, of x plus y plus z dz, dy, dx. Now, one thing that we can do here, if you remember in two variables, we said that if you have a function of two variables that you can write as a product of each variable. So, in other words, if you have like a function of x times a function of y, if it was over a purely rectangular region, so not a general region, but a rectangular region, you could split it up into the product of two Calc 1 integrals, two single integrals. You can do the same thing in three dimensions. So if you have a function of x times a function of y times a function of z, and if it's over a rectangular region, so it just goes x from number to a number, y from number to a number, z from number to a number, you can split that up as the product of three different single variable integrals. Now we can't do that here directly because it's x plus y plus z, but term by term it is. So we can kind of save ourselves a little bit of calculation here by doing a little bit of sneaky thing. So what we're going to do is break it up into each of the three terms. So it's the integral from 0 to A, 0 to B, 0 to C of x dz dy dx, plus this of y dz dy dx. And you may think, great, well, we split it up into 3. This looks almost worse than it did when we started. But now notice that each of these is a function of just one variable. So what that means is we can just integrate with respect to that one variable over the interval. And then what we do is we pick up the length of the interval, since it's just times 1 times 1. Right? So for instance, x is equal to x times 1 times 1, right? So this is really like a function of y. This is a function of z. 1 is a function of y, or it's a function of z. And when you integrate 1, you just get the length of the interval. So that means this first integral here, we do have to integrate the x squared. Sorry, we have to integrate the x to get x squared over 2. And that x squared over 2 is going to be between 0 and a, because that's where x runs. But then for y and for y and for z, we just get the integral of 1 from 0 to b and 1 from 0 to c. So that means we just get, b minus 0, c minus 0. And the same thing for these other ones. So for instance, when we integrate y, we're just going to get y squared over 2 as y runs from 0 to b, and we get a minus 0, c minus 0, and so on. You can see the pattern here, z squared over 2 from 0 to c, and let's see, then a minus 0, b minus 0. Okay, so what is this going to get us? So it looks like it's a squared bc over 2 plus ab squared c over 2 plus abc squared over 2. Of course, there's a lot of symmetry with each of these three terms. And we can factor out abc over 2, and you're left with a plus b plus c. So it's abc times a plus b plus c all over 2. So this is the mass. All right, so what we're going to do now is we're going to do the YZ moment. So the moment about the YZ plane. So let's go ahead and do that. So this is going to be MYZ. Now this is the integral from 0 to a, 0 to b, 0 to c. Instead of integrating x plus y plus c, though, we're integrating x times x plus y plus c. dz, dy, dx. But we can still use the same kind of trick that we had before. If I distribute this, it's x squared plus xy plus xc. And each of those individual, once I split it up into the terms, each of those individual terms will be function of x times function of y times function of z. So let's go ahead and do that. So we've got the integral of x squared plus the integral of xy plus the integral of xz. Need to move this a little bit. All right. So now this first one, it's only a function of x. So we're going to get x cubed over 3 from 0 to a. And again, the function of y is just 1, the function of z is just 1, so we get b minus 0, c minus 0. Now it's not going to be quite the same on the other ones. So for instance here, we do have to integrate x. So we get x squared over 2 from 0 to a. We also have to integrate y, though, and that gives us y squared over 2 from 0 to b. And the function of z is 1. So that is going to leave us a c minus 0. And then the last term is very similar to the second one. Again, we've got x squared over 2 from 0 to a. But now it's z squared over 2 from 0 to c. and times b minus 0, because our function of y is 1 now. Okay, so let's see. So what's going to happen is, for this first one, we're going to get a cubed bc all over 3 plus, then we're going to get a squared b squared c all over 4 plus a squared b c squared all over 4. Okay, so if we wanted to write this cleanly, let's get a common denominator of 12 first of all. So let's do this. So let's make this 12, 4, 12, 3, 12, 3. And then what can we factor out? Looks like we can factor out a squared bc over 12. So we can factor out, let's factor out a squared bc, and it's going to be over 12. And what's going to be left over then? It's going to be 4a plus 3b plus 3c, and this is all over 12. Okay, so now my claim is that now that we have this moment about the YZ plane, we really have the answer. We can just write down the answer for the other two. So why is this? Well, let's look at, say, the moment about the XZ plane. All we have to do here is just interchange the roles of X and Y, and which is going to interchange the roles of A and B. Right, so we're going to be integrating Y times, so this is going to be the integral from 0 to A, 0 to B, 0 to C of Y, X plus Y plus Z, dz, dy, dx. But notice, this is exactly the same computation we just did. If I just interchange, it's going to be A and B. So this would be the same as the integral from 0 to B, 0 to A, 0 to C of X. In fact, let me just write this out. This is the same as the integral from 0 to B, integral 0 to A, 0 to C of X. So all I've done here is interchange X and Y, and then that means that I need to interchange A and B. And so the overall effect is I get exactly the same result that I would before, except I have to switch the role of A and B. So what does that give us? Well, instead of having A squared BC, it's going to be AB squared C. Instead of having 4A plus 3B plus 3C now, it's going to be 3A plus 4B plus 3C. And it's still all over 12. All right, so if you didn't quite get that, you can work through the details if you want, but just think about switching X and Y and switching A and B. And then you should be able to also see then the last moment. Actually, you want to pause the video, see if you can write down, based on the pattern, what the last moment would be. So you should have seen that this is AB C squared times 3A plus 3B plus 4C all over 12. And now we can start to write what the coordinates of the center of mass are going to be. So, for instance, x bar. And actually, once we get then the general formula for x bar, you can again see you're just going to interchange the roles of A, B, and C, and we can just write down what the y bar and z bar are going to be. So x bar, this is m yz over little m. And we just said the myz, okay, we got that was a squared bc, 4a plus 3b plus 3c, all over 12. Now we have to divide by little m. So little m was up here. In fact, We were supposed to find the total mass. Let me go ahead and box this and note that it's the total mass. So we're supposed to divide by that, so it's multiplied by the reciprocal, so that would be 2 over ABC, A plus B plus C. Okay, so there's clearly a lot of canceling here. The 2 cancels 12. That's going to make 6. The entire ABC is going to cancel with this to make, well, just A. So we're just left with A on top. And, okay, so that's all the canceling we can do. So we're going to get A times 4A plus 3B plus 3C all over 6 times A plus B plus C. All right, so I think we can write down now the center of mass. So X bar, Y bar, Z bar is going to be equal to, so it's going to be A, 4A plus 3B plus 3C all over 6A plus B plus C, comma. Now, just realize that now for the X bar, it was A that kind of had the special role. Well, so we go to Y bar, it's like you're switching the roles of A and B. So that means we're just going to get, or you could just look at the formulas that we got above. So this is going to be B times 3A plus 4B plus 3C all over 6 A plus B plus C, comma, and then the last one then would be C, 3A plus 3B plus 4C, all over 6 A plus B plus C. Okay, and that is the center of mass. And I think it might be helpful just to plug in some specific values of A, B, and C just to get a feel for what this would be. So for instance, if A, B, and C are all 1, this is kind of like the simplest case. So if they're all equal, and we'll just say 1 is the simplest, then we would get X bar, Y bar, Z bar. So of course all the coordinates are going to be the same here. So you're going to get, 1 times 10, right? 4 plus 3 plus 3. So that's going to be 10 divided by 6 times 3. So that would be 18. So if you plug in A equals 1, B equals 1, C equals 1, you get 10/18, which is going to be 5/9. And the total mass, well, let's see. So the total mass, I need to go up here. The total mass would be 1, 2, 3 over 2. It'll just be 3 halves. Okay. So total mass would be 3 halves. We could do another example. Why don't we take, say, if A is equal to 1, B is equal to 2, C is equal to 3. So this is kind of the simplest kind of case where, all 3 of them are different values. So in this case, well, M would be, let's see, so it'd be 1 times 2 times 3, which would be 6, times the sum is also 6, so the product and the sum are the same. So 6 times 6 would be 36 divided by 2. So we have a total mass then of 18. And X bar, Y bar, Z bar. So I'll leave this calculation to you to verify, but you should get 19 over 36, 10 over 9, and 7 over 4. Okay. So that just gives you just kind of an idea with a couple simple examples for specific values of A, B, and C. But we did it for any A, B, and C, so you can use whatever A, B, and C you want here. So one thing to maybe notice in this problem, when you have a problem like this that's highly symmetric, so notice x plus y plus z, the density function is completely symmetric in x, y, and z. It's almost easier sometimes to to find a very general answer. In other words, if you had the problem where x was from 0 to 1, y from 0 to 2, z from 0 to 3, if you were given specific numbers, it might actually be less computation to do it with a, b, and c, because you could take advantage of the symmetry to reduce your computations and then you substitute in. So I think if you do it with specific numbers 1, 2, and 3 and you try and integrate these, it might actually be a little bit more work. So anyway, that's just something to notice about problems like this sometimes. So in this next example, we're going to look at finding the centroid of a region. So if you remember from Calc 2, the centroid of a two-dimensional region in Calc 2 was just the center of mass where you made the assumption that the density function was constant. So in that case, the rho just was a constant and it factored out. So we have the same thing in 3 dimensions. In fact, let's go back up to the first page. So for instance, if we look at x bar here, you could take the rho of x, y, z and take that completely out of the triple integral because it's just a constant rho. So it could just go, out like this. And you could do the same thing here. Rho comes out as a constant, and then the 2 rows cancel. So you don't need to know what the constant density is. You just need to know its constant density. And what you end up getting is just the triple integral of, so that goes away, that goes away. You just get the triple integral of x dv over the triple integral dv, over the area. So that's what we're going to do here. Just, we're going to assume that the density is constant. So the trickiest part of this problem is figuring out what the limit should be. And you can actually do this one of the 3 ways. So you can do it as what the book calls the type 1, type 2, or type 3 integrals. So the type 1 integral, you would try and project it onto the xy plane. The type 2 integral, you would project onto the yz plane. And the type 3 integral, you would project onto the xz plane. So I don't really care that you know this is type 1, type 2, type 3. That's not important. The point is you want to figure out one of the coordinate planes to project onto so that you can set it up as one of these types. So what I want to go through is, I actually think it's good to go through all 3 types here. So we're going to see if we can set this up all 3. And what you'll see is that one of them is going to be the easiest. Another one is going to be not bad. Not the best, but definitely not worst. And then the other one is not really good at all. So let's look first at what I think is the easiest. So I'll give you a minute. Think about, see if you can figure out what this looks like, and just try and set it up all 3 ways. This is really challenging. I think I can visualize it in my mind, but between my mind and the paper, I'm not very good at getting it from my brain into the drawing on paper. So I'll go to the CalcPlot 3D in a minute, but see if you can come up with what you think the limits for this should be for all 3 of them, and then decide which one you think is the easiest. Okay, so hopefully you had a chance to see how far you can get on this. Let me bring up the picture of what's going on here. So this is what's going on. Let me get the box out of there. Don't need that. Okay. So let me move it around a little so you can kind of see. There's a lot of moving parts going on here. And take a look behind it, over here. There's 3 planes. And then there's this cylinder. So the 3 planes are, there's the xy plane. Okay, so that's just z equals 0. So that is this one. That one there. There's the yz plane, which is x equals 0. That's the blue vertical. So we have the horizontal, one horizontal plane, one vertical plane. Then we have x plus z is equal to 1. That's a plane that's slanted. That's that one. Okay, and then we've got this parabolic cylinder, z equals 1 minus y squared. Okay, So there's all 4 of them. Now, the easiest way, I think, to set this up is to try and project onto the YZ plane. So let's look at it this way. And what you should see here is that, hold up just a second. Stop. Okay, so you can kind of see here, I don't have it exactly straight up and down, but you can see here in the YZ plane, it's projecting onto this kind of parabolic region above the y-axis. So let's go and see what that looks like, and we'll figure out the 2 limits for the YZ region. Okay, so here we are, and so this was at 1, -1, 1. And this was just a parabolic region, so it's something like this. It kind of looks like a semicircle, but it's not. It's part of a parabola. And so we were looking at the region inside here. Okay, very good. So now you have a choice about which order to take these, and I think one of the choices is clearly better than the other here. This is the equation of this. So when you hold x equal to 0, then what you get is this is z is equal to 1. Well, actually, z equals 1 minus y squared. So this is just where the cylinder intersects the YZ plane, and since it doesn't depend on x, it's just z equals 1 minus y squared. And it's clearly going to be better to fix y first, and then let z vary up and down. Okay, so that means we're going to let y range from -1 to 1. Z is going to go from 0 up to 1 minus y squared. Okay, so we're going to go y equals -1 up to 1. Z goes from 0 up to 1 minus y squared. And now we have to figure out where x goes between. Again, we're not worrying about integrating anything right now. We're just going to figure out some limits. So what does x go between what and what? Well, we have to go back to the picture. So let's go back and look at the picture and see if you can figure out. So if you're looking at it this direction, what you should notice is x varies from, so it starts off back here. It starts off at that blue vertical plane, which is just x equals 0. And then it goes all the way out to the green plane. The green plane is x equals 1 minus z. So that's telling us for a fixed y and z, x should range from 0 all the way out to 1 minus z. And that's the limits for x. And this is going to be, so whatever it is we're integrating here, it's going to be dx, dz, dy. Now let's go over why this is probably going to be the best choice. There's a few reasons. First, notice a couple of the limits start at 0. So the z and x start at 0. Whenever you have limits starting at 0, chances are when you go to plug in, things are going to wash away. So that's probably good. Also, we've got y running from -1 to 1. So that's a symmetric interval about the origin. That means there's a good chance that if we encounter an even or odd function, we can simplify things either by getting 0 or just doubling it and then going from 0 to 1. But the main thing is that all the limits here are just simple polynomials. There's no square roots. There's nothing like that. And so when you have that's good. And it's a single iterated integral. We didn't have to split it up into pieces. So it's just one piece. They're all nice expressions. A couple of them start at 0. One of them goes from -1 to 1. This looks to be really good. Now let's look at the other two, and you'll see that there's another way to do it, which is not too bad. It's not quite as good as this. So that would be projecting onto the xz plane. So if you project it onto the xz plane, hopefully this is what you got. So you should get this little triangular region connecting the points. Well, it'd be x equals 1, z equals 0, and z equals 1, x equals 0. So it's going to be this little triangular region right in here. Now, when you're projecting this way and you're trying to set this up as a double integral to get this region, or the iterated integral to get this region, I don't really think it matters whether you do x and then z or z and then x, because they're both going to be about the same. So let's do, I don't know, let's do x first. So let's let x range from, it's going to be from 0 to 1, and then z is going to go from 0 up to 1 minus x. All right, so we're integrating x equals 0 up to 1, and then z goes from 0 up to 1 minus x. Now this one looks even better than the first, maybe, but we run into a little bit of an issue when we get the y limits. It's not too bad, but it's not quite so nice, because, well, let's go to the picture. So we're projecting onto the xc plane, so we're looking at it this way. So you take a look straight on this way. Okay, there's a little triangle we were looking at. Now, what does y go between? Well, it goes between the two ends of this cylinder. Just imagine, you know, you're looking through here. So we have to solve for y. Well, that means y is going to be equal to, well, y squared is going to be 1 minus z. So we have to take the square root. So what we end up getting is a positive square root and a negative square root. If you take z equals 1 minus y squared, and you solve for y, there's two solutions, and they involve square root. So that's the problem here, is that we end up with a square root, which is not so nice. It's not too bad, but it's not as nice as the first setup. So we're going from minus root 1 minus c up to positive root 1 minus c. And this is dy dz dx. All right, now the last way is clearly the worst, and so let's see why. Let's look at the graph and let's see if we can project onto the xy plane. Okay, so let's look, and so we have to look straight down the z-axis. Let's look down this way. All right, so you can kind of see here, so you have to imagine, you know, what that region is that we're looking at underneath here. Notice there's clearly a boundary here where the cylinder hits this slanted plane. But the problem is that if I'm looking to see where z goes between, notice it changes. So, for instance, see this little piece under here? I need this little piece, so you can see part of the cylinder there. I need what's under the cylinder there, but below the plane. But then when I go under the cylinder, I want to go all the way up to the cylinder. So, sorry, I want to go just up to the plane. So I need to go to the one that's lower. So in this piece here, I need to go up to the cylinder. But then inside, where you can't really see, if I let me take off the cylinder, you can see. So inside there, see, I only want to go up to the plane. But then on the other end, over here, if I go all the way on the other end, of course, then I only want to go up to the cylinder again. So I kind of have to break this into 3 different pieces. This is really bad. So I can do this, and I'll show you what it is, but the problem here is this is going to break into 3 different pieces. So what ends up happening here, if this is 1, negative 1, 1, then I've got the parabola that goes out like this, okay, and like this. That's fine. And then I've got this vertical line here. Okay, so far that's not so bad. But now I have to think of 3 different pieces. So I'm going to split it up into, the main piece is going to be this one here. Okay. But then I'm also going to have a piece on the bottom and a piece on top. That I'll do those in 2 different colors. So I'm going to have a blue. I'm going to have, I'll say a green. And then I'm going to put the other one maybe in gray. Okay, so hopefully those are clear now. And so this right here is the graph x is equal to y squared. Okay, so let's see. We have to do 3 pieces here. So let's do the blue one first. The blue one's the easiest. That's just y from negative 1 to 1. x is going to go from, okay, so it's going to go from like here to here. So that's going to be from y squared up to 1. Y squared up to 1. And then z, now remember that inside this part we had to go up to the plane. So we only wanted to go up to the plane, not the cylinder. So that's going to be from z equals 0 up to that slanted plane, which was z equals 1 minus x. And this is dz, dx, dy, plus, now we're going to have another piece here. Let's look at, say, the green. So for the green, y goes from 0 to 1. And x is going to range from, so here it's going to be something like from here to here. So that's going to be from 0 up to y squared. And then lastly, z is going to go from 0. So on either side here, the green or the gray, we have to go up to the cylinder, which is going to be 1 minus y squared. So z from 0 to 1 minus y squared. And then we have the third one. So we're going to have plus another one, which would be the integral from, so this time it would be from y equals negative 1 up to 0. And actually the other two are going to be exactly the same. So x is then still going to range from 0 to y squared, and z is going to go from 0 up to 1 minus y squared, dz, dx, dy. Okay, so I think it's pretty clear this is not the way to go. And I think the first way is the easiest. So let's partition off all of this. So you didn't have to go through all this. Once you saw that the first way was probably going to be pretty good, you could just stick with that. You didn't have to. I was just doing it to show you the 3 different ways. It's kind of a good exercise to try and figure out the limits. So let's go back up here. All right, so we're going to do this first way. So it's just a matter of carrying out the computations at this point. So let's do the mass, m. So m is going to equal, so it's the integral from -1 to 1 of the integral from 0 to 1 minus y squared, and then the integral from 0 to 1 minus z, dx, dz, dy. Okay, so when we integrate with respect to x first, so we just pick up 1 minus z, because it's the integral of 1 is just the length of the interval. So now it's -1 to 1, 0 to 1 minus y squared of 1 minus z, dz, dy. Okay, now there's a little integration to do here, so we have to integrate 1 minus z. That's going to integrate to z minus z squared over 2, and we have to evaluate this between 0 and 1 minus y squared. 0 is not going to contribute anything, so we're going to get the integral from -1 to 1 of 1 minus y squared minus, now I'm squaring 1 minus y squared, so I can switch that around and just say that that's y squared minus 1 all squared over 2. All right, there's a little bit of multiplying out to do here. -1 to 1. 1 minus y squared. Well, actually, let's stop. Stop and think. What can I do already? Plug in minus y into this. You can already see that this is going to be an even function. The only powers of y are 2. So this is even. So I'm going to immediately switch this and make this 2 times the integral from 0 to 1. 2 times the integral from 0 to 1 of, okay, now it's 1 minus y squared minus, okay, it's going to be y to the 4th over 2. So minus a y to the 4th over 2. It's going to be minus 2y squared over 2. So that would be minus y squared, but it's minus that, so plus y squared. And then finally, plus 1/2 but then it's minus, so minus 1/2. All right, and so what does this get us? Twice the integral from 0 to 1. Well, actually, let's see here. These are going to cancel. 1 minus 1/2 is just going to leave 1/2. And then I can take out the factor of 2, and the 2, that'll cancel with what's out here. So I'll just leave 1, that'll go out. So this actually cleans up quite a bit. So overall, we've got, it's just the integral from 0 to 1 of, there's not much left over. Let's see, 1 minus y to the 4th. Okay, so it's going to be y minus y to the 5th over 5 from 0 to 1. And so it's going to be 1 minus the 5th. Looks like we're going to get 4/5. Okay, so that is the mass. Well, I mean, it's the mass if the density function was identically 1. If the constant density was 1. Really, if you keep the rho in there, it would be 4/5 times rho. But we're just assuming rho is like equal to 1. So let's go ahead and compute the other ones. How much room? I think we have enough room here if I write small. So let's look at the moment about the yz. Okay, so this is going to be the integral from minus 1 to 1. 1 minus y squared. 1 minus c. Now we're integrating x. dx, dz, dy. Okay, so now when we do this, we do have to integrate x. So this is going to be x squared over 2. So x squared over 2 from 0 up to 1 minus z. So I can pull the 1/2 all the way out. So I get 1/2, the integral from negative 1 to 1, 0 to 1 minus y squared. And again, the 0 doesn't contribute anything, so I'm going to get 1 minus z all squared, which is the same as z minus 1 all squared. So z squared minus 2z plus 1 dz dy. Okay. Now I have to integrate with respect to z, so there's quite a bit more integration here. Minus 1 to 1. Z cubed over 3 minus z squared plus z. All from 0 up to 1 minus y squared. All right, so this is a little bit more involved. Negative 1 to 1. Again, the 0 is not going to contribute anything, so I'm going to get 1 minus y squared all cubed, 1 minus y squared all cubed over 3 minus 1 minus y squared squared. Again, I can switch the order because it's an even power, and then plus 1 minus y squared. So admittedly, this one is kind of a mess. Let's see. Yeah, maybe we will only need another sheet. So let's see. This is going to be 1/2. Again, there's only y squareds involved, so we can go ahead and say, since this is even, that'll cancel the 1/2. So we're just going to get the integral from 0 to 1. Integral from 0 to 1 of... Okay, so the first one, the binomial theorem, that's going to multiply up to 1 minus 3y plus 3y squared minus... Oh, sorry, it's going to, because it's y squared, so it's going to be 1/3 minus 3y squared, so over 3, so minus y squared, plus 3y to the 4th over 3, so plus y to the 4th, and then minus y to the 6th over 3, and then minus, we got the y squared minus 1 squared, so minus y to the 4th, plus 2y squared minus 1, plus 1, minus y squared. Okay, what a mess. But again, this is the best way out of the three. So let's see, I have a feeling a lot of this stuff goes away. Yeah. Okay, y to the fourths go away. Oh, we got 2y squared minus y squared minus those go away. A lot of stuff goes away. 1 minus 1 goes away. So it looks like all we're left with is, 1 minus y to the sixth over 3. So I'm going to take the 3 out, take the 1/3 out, and then integrate. Right, so 1/3 integral from 0 to 1 of 1 minus y to the sixth. So it's going to be 1/3. We got y minus y to the seventh over 7. 0 to 1. And that's going to be 1 minus 1/7. So that's going to be, looks like 1/3 times 6/7. Which of course is going to be 2/7. All right. Let's just talk about the next moment. So let's go on to another. Well, actually, let's do m x z. So I claim that this is 0. So I'm going to leave this to you. So I'm going to convince yourself why this equals 0. So I want you to convince yourself physically. So I mean graphically. Go to the region, look at the region, convince yourself geometrically why this moment should be equal to 0, and then take a minute and just do enough computation so that you can convince yourself algebraically why it's 0. But it does end up being 0. So that leaves just one last moment. All right, there. Magically, I have another page. So let's look at m sub xy. So this is integrating 0, 1 minus y squared, 0 to 1 minus z. And this is z dx dz dy. Again, since z is constant with respect to x, I just get z times 1 minus z. But now I'm integrating with respect to z, so now I really do have to integrate. And so I'm going to get minus 1 to 1. This is going to be z minus z squared. So it's going to be z squared over 2 minus z cubed over 3. And let's see, we're going from 0 up to 1 minus y squared. All right, so this is going to be negative 1 to 1. Again, y squared minus 1 all squared over 2 minus 1 minus y squared cubed over 3. Okay, now I'm going to do a couple things here. These are just little algebra tricks. Again, this is an even function, so we've done this a couple times. But there's something else I can do here. I can make this plus, and then when I change the sign of one of these, so it'll make one of these 1 minus y squared minus 1, and I'll have 2 left over, and since that's an even power, then I can just replace this with y squared minus 1. So this is the same as plus y squared minus 1 cubed. Now, why would I do that? Well, it's going to be easier to multiply this out because now I can kind of, well, I'm going to get a common denominator, and then I'm going to factor out a y squared minus 1 squared. Now, if you don't see these little kind of shortcuts or tricks, that's fine. I'm just showing you kind of some little things that I can do just to save just a teeny bit of time. Okay, so we've got the twice the integral from 0 to 1 of, now what I'm going to do is factor out y squared minus 1 all squared over 6. So what's left over? Well, I've got 3 plus, so the 6, that'll come out as 1/3 out here. And the point now is that I can kind of, distribute across here, and makes it a little bit easier maybe to simplify. Okay, so we got 1/3, 0 to 1. Okay, so I'm going to square that. It's y to the 4th minus 2y squared plus 1 times, and this is going to be 2y squared, and then we've got minus 2 plus 3. So that's going to be 3 minus 2 is 1 plus 1. Okay, now we just have to FOIL this out. Now, this seems like a lot, but I think it would be even worse if we tried to do the perfect square trinomial and the cube, and then combine all the terms. I mean, either way, it's not the best. Okay, so this is 2y to the 6th plus y to the 4th. We get a minus 4y to the 4th. We get a minus 2y squared plus 2y squared plus 1. And a lot of stuff cancels, as usual. These make a minus 3y to the 4th. Okay, so this is going to integrate to 2y to the 7th over 7 minus 3y to the 5th over 5 plus y from 0 up to 1. All right, so this is going to be 1/3, 2/7 minus 3/5 plus 1. All right, so we need to get common denominator here of 35. So that's 45 minus 21 is going to be 24. All right, so 8 over 35. Okay, so we've got all of the moments, we've got the mass. So let's figure out now x bar, y bar, and z bar. So x bar, this is m sub yz over little m. And this is, what was that first moment we got? 2/7. Yeah, okay, 2/7. And I believe the mass that we got was 4/5, which means we need to multiply by 5/4. We're dividing by 4/5. So that's going to give us, after some canceling here, 5/14. Okay, and we already said, so y bar, we know that's 0, because we got the moment about the xz plane was 0. And then for z bar, this is mxy over little m, which is the 8/35 divided by 4/5. Again, a little bit of canceling, 2/7. 2/7. Okay, so it looks like our center of mass, we finally got our center of mass here, which is the centroid. So the centroid is x bar, y bar, z bar is equal to 5/14, 0, 2/7. Woo. Let's go back and just, I'm just going to plot this point. We'll have to make it translucent so we can see through, but I'm going to just plot this point just so you can see where it looks like in that region. Okay, so there it's kind of hard to see in there, but you can, okay, so you can kind of see what that region looks like. These are supposed to be translucent so you can kind of look through them. All right, now here's the point. Where'd it go? Right there. Okay. Yeah, you can kind of see it in there. Again, it's inside all these things, so it's kind of hard to see inside there. Maybe so here's what we can do. I'll take away one each at a time, and you can kind of see it. So if I take away the cylinder, maybe, okay, there it is right there. So it's right there, okay? And there it is. You can see it now, but when I put the next plane in, you're not going to be able to see it anymore because the plane's going to be covering it up. And it's gone now. Okay, so it's inside there. So it seems about right. All right, so this was a lot of work. What we're going to do next is cylindrical and spherical coordinates, and I think what you'll see in these other coordinate systems is, although there are other coordinates that are not rectangular coordinates, what often happens with those two is two things. First, the limits tend to be numerical values, so that you don't have an expression or a function for a limit. And that's just because you're actually working over regions that are just bounded by constants. The other thing is that in the other two coordinate systems, you generally get products of the functions of one variable. So for instance, when you're doing spherical coordinates, you often get just like a function of r times a function of z, or maybe you get in spherical coordinates a function of rho times a function of phi. So that turns out to be actually computationally easier than some of these rectangular coordinate problems. So that's what we'll do the next couple of videos. We'll look at some examples of triple integrals in cylindrical and spherical coordinates.